Thank you very much for giving me the opportunity to present my research. So the research is impact of EV charging and space heating on distribution systems. So this is an analytical research project that aims to explore the impact of different parameters of electric grid components on probability of failure, consequence of failure, and overall network risk. In collaboration with ESPEN, this research project aims to provide ESPEN with insights into the impact of asset management decision process defined by the monetized risk model and inform the future investment strategies which may be introduced as a requirement for the next round of price control, RIO 3. So the impact of electric vehicles and specific on distribution systems, the electric vehicles share in transportation is increasing every year. In general, the electric vehicle load is 7 kilowatt for slow charger, charger load is 7 kilowatt for slow charger and 50 kilowatt for rapid charger and 250 for superchargers. More use of electrical vehicles in future years can influence the maximum and average demand. So this will account for the higher electrical stress on transformers, and therefore the electric vehicles has the potential to stress the distribution and transmission transformers. Okay, so the general definition of end of life for an insulation system is a point at which the insulation can no longer perform reasonably. So here we see that the maximum demand, when it is increased over 130%, the transformer end of life can go to number 3 instead, whereas if the maximum demand is remaining less than 120%, it can be 1. So the maximum demand should be kept less than 120% to have a longer times lifespan of a transformer. And for the average load, we see that less than 80% average load on a transformer is very good. Instead, if we have a higher average load, overloaded transformer, then it will be lifespan will be significantly shortened. And we see here in summer days, the transformer can be significantly loaded with the high penetration of the electric vehicles, and in the winter it can be even worse, where it can be over 150% loaded, and that will affect the transformer health significantly. And because the transformer is the most costly instrument for a transmission and distribution network, its lifespan is very significant for that case. So from the data we have received from ESPEN, I have simulated this model and simulated this chart. So from the NORMS model, we see there is established relationship between probability of failure and end of life. So end of life scale is from 0 to 0.5 to 15. Higher is worse. So a transformer with a maximum demand more than 120%, we see the number of end of life can be around 3 for a specific transformer. This is not for all the transformers, but that's moderately loaded transformer. So for the average load, I have already explained this graph. So here we see that it's important to estimate the EV charging demand. By superimposing the estimated EV charging demand and space heating demand on the currently available power demand, we can estimate the increase of overall network demand. And then we can estimate the increased aging rate of a network asset, for example, transformer. And then moreover, we will be able to estimate the whether the current infrastructure will be able to withstand the increased demand, or does it need to be upgraded. So to estimate the overall increased demand, so we have simulated that if we charge the EVs for 3 hours a day, then the increase of demand can be from in Esprango Valley. It can be from 10 megawatt to 15 megawatt. It has been simulated for 3 hours in different times of the day. So it has been for this blue line we have simulated for the midnight, and then at different times of the day. So if we simulate for 6 hours, then we see the maximum demand increase is less. Before we have seen 5 megawatt hour increment, but here it is around 2 megawatt hour increment. That's better for the transformer. So it is better to charge the EVs on a on a higher time span instead of a short time. So another aspect we need to consider is space heating. Space heating without any electric heating in a house, we see the average maximum demand can be 600 watt. But if we have additional electric heating, then it can be 900 watts. And if a household has only electric heating for primary purpose, primary electric heating, then it can be up to 2 kilowatts, and that's significant. And a simulation we see that it can be up to 64% of the entire energy consumed by a household. So both of these aspects need to be considered for the health lifespan of a transformer. So we will estimate the overall demand for the electric vehicles and space heating for this research, and identify how we can reduce the overall load demand in the network and increase the lifespan of the transformers and other network assets. Thank you very much.
Thank you very much, Arshad. Very efficient with time. So that's and very important piece of work. So let's have some questions, a couple of questions for Arshad. Who would like to start? Yes, Alex. Okay.
Hello, Alex from ETP. A lot of the work sorry, we're recording. Hello, Alex Reid from ETP. I'm interested in your presentation. A lot of the work I do at ETP focuses on transport, electrification of transport and EVs. And just kind of absorbing your presentation, I'm interested to know, when you're looking at transformers and the aging of transformers, what analysis you're doing in terms of the difference between the location of those transformers in more rural areas, rural communities versus urban, because it might be fair to say that it's the transformers in more rural areas that perhaps aren't being invested in quite so much, and potentially at more risk, perhaps, and vulnerability when more people are charging their EVs. So I just wonder, have you done any analysis locationally, spatially, at some of the vulnerabilities when it comes to transformers in different locations?
Yes, I see in the data set that we have used is Sprangho Valley and Devilmore. The average loading in that area is 16% to 30%. And if we superimpose the electric vehicles and the space heating in that area, it doesn't go over 60%. So we see from the simulation, it doesn't affect those transformers significantly. But if we consider about Glasgow or Edinburgh, then the transformer here is already significantly loaded. For example, at more than 60%, 70%. But if we have more, double of this amount, then this transformer will stress so much, and we will need to invest more in these areas to reduce the network risks. Otherwise, if the transformer is any transformer is blown, then obviously there are so many costs related to it.
So if I understand correctly, are you highlighting that it's more likely to be in higher population density urban areas?
Yes.
Where there's more risk?
Yes.
Compared to lower density population areas in rural areas? Okay.
Yes.
Okay, thank you.
Okay. Thomas, very short question.
I was just interested in, I guess, in your model of the transformer aging, do you consider the impact of voltage on that as well, and sort of and I guess the link between like instantaneous failure versus this kind of aging characteristic?
No, I haven't considered the voltage at this moment. I just considered the thermal stress, because the thermal stress will stress the insulations, and we have literature knowledge from there.
Okay, thank you very much, Arshad. Very important piece of work, so thank you very much for sharing that with us. Right, Mohammed, we're ready for yourself. Mohammed's from Glasgow Caledonian University and is working on a digital twin. Perhaps, I think you've got a poster outside.
Yes.
So maybe you've already had a look at that, but we very much look forward to your presentation. Okay. Thank you.
Hello everyone, my name is Mohammed Numair from Glasgow Caledonian University. And my PhD project I just started 6 months ago is about creating a digital twin for future distribution networks with smart meter data driven and control. So the project background starts from what's called low carbon technologies that are being embedded in our distribution network. And these are the small scale generations such as rooftop PVs or small wind turbine farms and electric vehicles and heat pumps. And all of that is being integrated for the obvious reason that we need to achieve our target of the net zero by 2050. But the problem is that these low carbon technologies are introducing the network to some of the issues that are such as bidirectional power flow, voltage variations, and harmonics and power quality issues. So my project aim is to use the physical distribution network that we have and the already existing, and the country has already invested in smart meters network and smart meter infrastructure, and only with the data from these smart meters, without any additional equipment, we can create what's called a digital twin. So we can create a digital twin that receives real-time data from these smart meters and gives back by optimizing the operation of the whole distribution network. And this puts us to the aims of my project, being creating a data-driven approach for monitoring and management of network assets, and also creating a digital twin that will give us, that will be able to make us optimize the function operations of the network as a whole in making network reinforcements or predicting, mitigating faults. Also on the asset level, we can improve the condition monitoring and predictive maintenance, such in the case of transformers or cables. So my project plan so far is to start from taking insight and benefits that we can extract from the smart meters network. And after that, I will be working on the detailed modeling of transformers and cables, the lead assets in any distribution network. And then I will try to model what the effect that these low carbon technologies can introduce the network to. That will lead me to be able to make a holistic digital twin of the entire distribution network and see what effect these low carbon technology can do. Finally, I will be able to validate these benefits to my industrial sponsors and start my writing up. So far, I just been in the first phase or the first work package on my PhD, which is trying to use the benefits of the existing smart meters. I had a really good time researching this topic because the UK had a really good program called the Smart Metering Implementation Program. And this program is already have connected 13.8 million homes around the UK with smart meter network. Each home has its own smart gas and electricity meter, and in-home display that shows the consumers their electricity. And all of these data inside the home area network or whatever data about the consumption in-house is communicated to a central national smart meter company called the Data and Communications Company. And then from that company, it starts to give the data to respective energy suppliers and distribution network operators. So I started by extracting the benefits from that program and what benefits we can get. So first of all, the consumer, because it's the main target of the regulator. He will get, any consumer with a smart meter would get more accurate billing. The in-home display is really a good thing for improving your energy consumption. You will be able to relate what devices are causing you to pay more bills. Also, it's now easier than ever to switch between energy suppliers, which increase the competition between them and gets you to more flexible tariffs. For the electricity suppliers as well, there are a lot of benefits, such as automated metering, automated meter reading without sending a reader to the consumer premises, as well as being able to remotely service any consumer at any time, which reduces the customer calls and the cost related to that. It also enables them to make better frequent billing, and also in the future there will be some demand-side management or demand response program. All of that will lead to the national benefits of upgrading the infrastructure to achieve the net zero goal, also the digitalization and flexibility targets for a future smart grid. But now for the benefits for distribution system operators, and this is the focus of my PhD since I am funded by one of them. So the target, or like the different phases of my PhD would be related to each one of these benefits. So the first, fault and mitigation and quick supply restoration possibility using smart meter data is what I will be showing in this presentation. And the rest of them, such as network reinforcement and using digital twin for active network management, will be discussed. I will be trying to work on them later on my PhD. So for now, my question is very simple. Can smart meters reading to be able to locate a fault in a distribution network? And that found to be a very critical issue for distribution system operators that will save them a lot of time and a lot of money. And because they need to use advanced equipment such as phasor measurement units, current sensors, and other equipment. So if a smart meter can do the job, it would be a very good opportunity. So now I have to validate this idea using a distribution system, the IEEE 13 bus, and I simulated 32,000 fault scenarios using different variations from fault location, load variation, and fault resistances. And using this big data set of fault location and smart meter reading, I can feed it into different machine learning models and see if these machine learning models will be able to use just the smart meter readings around the system, these yellow boxes, to locate where the fault is. And these are the results, and they were actually very promising, since starting from the decision tree, which is the simplest machine learning model, it gave me accuracy of 62%, and going up to the KNN, which had a higher percentage, 86, and the best of them was the random forest at 95.6% accuracy. So in general, the smart meter readings were able to define where the fault is with a high accuracy. And then I became greedy. I wanted to make it more granular. So I went to 10 feet accuracy. If it can, 10 feet is like 3 meters. Can it locate the fault at 3 meters? And that was possible, but with decreased accuracy at 75%. So finally, this is where I am in my PhD at this point. And the preliminary results were very promising that we can use that. And it is theoretically possible to use smart meter data to locate a fault, but is it practical? That's what I'm waiting for, to get some data from the Scottish Power Energy Networks to be able to validate this practically, and then I will progress to the next part of my PhD. Thank you, and any questions I appreciate.
Thank you very much, Mohammed. Questions for Mohammed? Yes, please.
Thank you for the presentation. Thank you for the presentation. It was very interesting. So I have 2 questions, but they're very quick. So first one is, what simulation tool are you going to be using for that digital twin?
Yeah, I used Simulink for now. Yeah, and there is another software that uses Python called IPSA. So that I'm investigating that as well.
Perfect. And second is very quick as well. Is here you just had one fault. Does it make any difference if you have multiple faults within that?
Yeah, that's actually in my action plan. I will try to simultaneous fault as well as different faults. So this is 3-phase fault. I will try just line to ground fault, different types of fault. So that's I didn't do yet, but it's
perfect. Thank you very much.
Okay, thank you. And a question over here.
Thank you. Very nice talk. So I was wondering, what information do you get out of the smart meter to be able to identify the faults?
Yeah, for this scope, the IEEE system, I just used active and reactive power, import and export, because when I looked at the specification of any smart meter, this is the data that it can give. But I found that it also provides some voltage quality measurement that can be used later on. Yeah.
Okay. Thank you.
Yeah, no worries.
Okay, thank you very much. And one last question here. Yes, thank you.
Hi, Mohammed. Very interesting talking. I just wonder, what's the time scale of your smart meter?
The time scale of measurement, or?
Yes, for example, you collect data every minute or every seconds, something like that.
That's a really good question. So smart meters in general send data every half an hour. So in order to be able to locate a fault, that's actually a challenge that you needed to be able to read the instant of the fault. So that's what I'm looking into right now. Is it able, and that's actually taking part in my next discussion with Scottish Power. Are we able to capture the moment, the instant of the fault in the smart meter readings? That I will know from historical data. Yeah.
Okay, thank you very much.
No worries, thank you.
Great, thank you very much. Excellent, Mohammed, thank you. Very good. So let's move on to our third presentation. And Taimur, why don't you come up? Taimur's from the University of Strathclyde. Very good, thank you.
Thank you very much. My name is Taimur from University of Strathclyde, and I'm just finishing my first year of PhD, ending in second year, obviously. So I have worked on the some preliminary stages on the low voltage DC microgrids. So when they are operated in a islanded, they don't have a support. So sometimes when we are connecting the power converters, they have the voltage and current issues. And some power stability, so we have worked on that. But some outlines for we have the background and motivation, and then the system preliminaries, and we have basically worked on the controllers. So I will be discussing our proposed methodology and some simulation results. The motto is again, so we are like moving towards the sustainable power sources, so to make the environment clean, and obviously we need a clean energy to support the environment. So for this, obviously we need the power from the non-conventional power sources, which are, for example, the wind and PVs, and some from the tidal. But we know that they are quite nonlinear. So, for example, if we need a DC microgrid, so for that, their connection to the common point of coupling is quite difficult in terms of if we are using our controllers and all those things. So for that, from the literature, like different methods have been proposed, amongst which DC microgrids are the most prominent one for the DC systems, and different control algorithms have been proposed as well, but they all have their pros and cons. So normally they can be operated in centralized and decentralized, and for example, if we see the inverters and some controllers from a very famous company, so they are using this master slave and rule based controllers. However, this is like an industrial approach. So how quickly we can adopt that control algorithm and that mechanism to that can efficiently stabilize the DC bus voltage in islanded mode operations, and as well as improves the voltage and bus profiles. So for example, if we see this is the profile voltage from the previous methods, from the decentralized and the master slave method. So obviously they just gives the some voltage ringings, and on the back end when we see, so we have the problems with the hardware when we are accessing the power sources, or we don't see that, but actually this happens and damage our equipment at all. So for this motivation, we are using the a bit advance of the controller family, that is the nonlinear families of the controllers, so some frictional order, and then the industrial grade PID, we are combining that one with this, and then obviously neural network based very simple approach is used, so that actually detects any sort of a disturbance in the whole system in the low voltage DC microgrids, and then it actually try to stabilize the DC voltage in the in finite time. So for example, this is just a very short system overview. For example, we have the DC sources connected to a common bus, and through obviously through some line that has the resistance and impedance of the converter as well. So obviously this varies with the temperature and different environment conditions, which actually cause the voltage deviations, the current problems, and some voltage rings as well. So we have identified those with the conventional one. We have those problems, so we are trying to resolve that issue with just a bit step of higher controller, but still that is like more implementable at industrial level. So the controller is basically, it takes just the parameters of the each one converter, it automatically detects our user interface, and then some using some mathematical equations, we just model the overall controller, and then we are taking it to the a bit just a complicated one mathematics. Just because in this sort of controllers we have the voltage and current chattering, so that actually is not stabilized. So we are taking it to the frictional order levels and introducing that one into the controller. But this is still like implementable in the inverters and converters, for example, by the Siemens, or for some famous inverter companies. They are still doing that. So with the adaptive troop one, we are actually what we're doing that we have developed the industrial grade controller, which actually takes that those information. For example, if there is some sort of a disturbance, or the line has been shifted or has been extended, so line resistance or impedance has been changed, so it actually automatically detects that and adjusts the overall gains of the controller. So it just provides us the complete the voltage and current across the pivot point. So obviously a bit more mathematics there, but I have to skip. So these are just results from the conventional methods which are used in the nowadays inverters and controllers that use. So for example, if we are using them in a parallel versions, 3 or 4 DC sources are interfaced to a common PCC. So obviously when we have a sudden load change over there, so I have used a 60% load variation, we can see at 0.3. So that actually we have the variations in the current and the voltage profiles, although they should have been sharing the same load current, but the controllers and the converters becomes destabilized. So comparing with our proposed one, so where we see that we are actually making the converters and the controllers to communicate at very low bandwidth communications, to exchange the informations about the currents, and then trying to enhance their equal current sharing. Sorry. So on the right side, if we see in the top, so these are the current and voltage sharings in a proposed method. So we can see that quite efficiently they are sharing, and then the same topology, the same method is used with the other controllers in a distributed way. So we see that there is quite variation. Similarly, is for the current sharings for the for maintaining the bus voltage. If we see, so we do have the variations in terms of the current for the distributed one, and if we see over here, so in a very no matter of time, it just track its reference and is sharing the load current for all R. So all this was tested for the light loading conditions and heavy, and we see that the proposed method is providing us quite promising results. And the last one is the for the disturbance. So if we change the line, or suddenly in our low voltage DC microgrids, we are just connecting something abruptly disconnecting. So if it is affecting those sources, so we see that the red and the blue traces are the proposed one, and it quite efficiently rejects disturbance and adjusts its gains for the controller. So the power sources are giving obviously the very straightforward what is told, so they are giving the power. So in conclusions, the parallel power converters, when we are connecting our power sources, they do have the problems of sharing the equal current and maintaining the bus voltage, which is important thing, and from the previous studies this was not done. So an industrial approach was needed, which is proposed here, so to maintain the exact bus voltage and enable the power converters to share the proportionate current and load. Thank you very much. Any questions?
Okay, Timer, thank you very much. Do we have a quick question for Timer? No. DC microgrids, which applications do you think we'll see more of those initially, Timer?
For DC microgrids, yeah, I mean, we are moving more towards this. So for applications, we have the EVs and sometimes the islanded grids in the rural areas. So over there we have their potential applications, and maybe if we are extending it, so like in the high voltage we can extend it, but at the moment the DC microgrids have their applications in the rural areas.
Okay. Thank you very much then, Timer. Thank you.
Thank you.
Okay, and on to our last presentation. Hopefully everything is okay with it. Oh, there we are. Excellent. Great. Andreas, from University of Edinburgh, look forward to your presentation. Thank you.
Yes, thank you very much for that introduction. I hope you can hear me all right. Today I'm going to say something about the research that I've been doing for the last 4 years. Just started in my 5th year for my PhD. I'm a part-time student, which is equivalent to me just having finished the 2nd year. My name is Andreas Lindemann. I'm from the University of Edinburgh. I'm a student at the School of Social and Political Science. My degree is in Science and Technology Studies, and my supervisors are Ronan Bolton and Mark Winskill. Let me see if that works. It does. So the field that I'm doing my research in is the transitions research. So it's more social science focus that I'm looking at. And in the field currently, most of the research that I'm looking at is on disruptive niche technologies. So things like local electricity networks, for instance, and how they might change electricity systems from the bottom up. But my argument is, in my research, I'm looking at large HVDC power cables connecting countries and large connections within countries. So my argument is that when I look at these in particular, we need a larger perspective, and we need to look at more central actors taking the decisions here. And similarly, the research says that in order to understand whole system, in order to understand multiform system dynamics, we require a whole system perspective. So that helps me in providing my grant for my research. And the idea itself is not new. So large technical systems is a field in research which has been driving the field in the 1990s, and starting from 1983. So that is something that's really helpful for my research. And one notion is that of reverse salience. That is a term that is derived from war terminology, where you have a front line which isn't able to proceed because one element of that front line falls behind. And this element needs to be fixed before the whole front can move forward. And I'm coming back to that later. So what has been said this morning is that Scotland has large potential for renewable energies. And this is something that I want to draw to, because in the chart or in the graph you can see on the very top a violet color in Scotland, and that means we have brilliant resources for wind, and we have potential for water resources as well. So wave and tidal, for instance. So Scotland can be part of the solution to reach carbon targets in Scotland and the EU, so in the UK and the EU. And in order to be able to do that, we need cables to transport that electricity. At the moment, even the capacities south to England are constrained sometimes. So I don't think I need to tell you much about the work that TNOs do. And yeah, something that I found in my research is that the question of cost allocation is quite decisive in these projects. So when I look at these 4 projects, 2 are not realized yet, 2 have been already implemented. It's quite decisive how questions of cost allocation were targeted. So that's why I'm drawing it at the next slide. I'm just going to introduce you to 2 projects that I'm looking at, both starting in Norway. So these are 2 interconnectors. The one is Nordlink, which starts in Tonstad, Norway, and goes to Wilster, Germany, quite close to where I'm from. It's 623 kilometers long, has a capacity of 1.4 gigawatts. The project costs are estimated somewhere near 1.5 to 2 billion euros. It's got a voltage of 525 kilowatts. And the status is the planning started in 2007. 2015 there was a final investment decision, and in 2020 the first power flows were operational in the cable. And then on the other hand we have North Connect, which is a project going from Norway to Scotland, starting in Malden, going to Peter. It's got a length of 650 kilometers, so quite comparable in length, but also the capacity and the project cost. The status of that project is it started 4 years later, and in 2020 it was put on hold by the Norwegian government. So now I'm getting more to the insights of these projects. So this was more kind of the general data. So for NordLink, one of the challenges was there was a separate cable planned also to Germany, and the planning for that cable started a year earlier. So I was looking in the political decision why this cable was not successful and this one was. And so one decisive point of decision for NordLink was when TenneT, one of the TSOs or TNOs in Germany, who's involved in the project, announced that it has not enough capital available. The German government stepped in and intervened and bought half of the share of the project through its investment bank, KfW. So a central actor coming into the mix and driving the project forward and getting involved in order to make it possible. And this commitment by the German government actually made it possible for the link to go forward. With North Connect, we have a decisive moment in 2013 when SSE pulled out of the project, because that's a moment when there's no direct British investment anymore in the project. It's only Scandinavian planners of the project at the moment. It was placed on hold by the Norwegian Ministry for Petroleum and Energy in 2020. And what they say at the moment, so the argument why this whole project was stopped, is that they want to assess the short-term impacts of the existing interconnectors on their electricity prices first. And the government recently said that this process will not be finished in the period of government. So it takes quite a time to assess the impact and the cost that impact the northern end of these interconnectors. What happens at the moment is, due to the gas crisis that we have in Europe, we have extreme electricity prices, as most of you will know, and these electricity prices are transferred through these interconnectors to the north, because in the northern, in the southern bidding zone in Norway, the cheap electricity is transferred to the south, while the expensive electricity from the south, or that way the cheap electricity will be sold to the south and the prices rises. So that is one of the challenges for North Connect at the moment. And so what I'm doing is I do have a couple of interviews with political actors, with researchers, with industry experts, consultants, so different groups of people who are involved in these processes around the full project, and to hear about their views. And I brought you some examples for North Connect today, so the project which has not been realized yet. So one thing is that what's mentioned quite often in these interviews is that affordable access to hydropower is perceived as family silver by Norwegians. So I've read in documents 3 or 4 times that it's comparable to gas prices in the US or driving really fast on the German Autobahn. That is something that it's quite hard for policy to touch that. And so the cheap electricity prices and the cheap access to hydropower is one of the decisive things in Norway, driving resistance, for instance, by industrial actors. Because they don't want to be threatened by higher electricity prices, and they want to stay competitive in the European competition. The second thing is It might be too late to find a rational solution to a rational problem, which is cost redistribution. In Norway, we say it goes politics in it. You leave the technical, the rational sphere, and it has sprung to politics. So these links make perfect sense from an engineering point of view. From an economic point of view, it's really interesting because Norwegian electricity producers can sell their electricity to mainland Europe, and they benefit from the high prices in mainland Europe. But now that it's not about economic or engineering topics, it's a political decision. And the third thing is there's no way this project is going forward. This is an opinion by someone I was talking to. And on the other hand, we have, this is the last quote, we have quite an optimistic view in the UK that North Connect can still be realized. But I think I finished my time. So thank you very much for listening. In case you want to contact me, here are my contact data. And if you have any questions, feel free to ask them.
Thanks, Andreas. Very interesting topic, very challenging topic. I was over in Finland last week, and they were talking about some of the issues around those interconnects affecting local prices. So very pertinent, and particularly heightened by the cost of living crisis just now, where it's highly sensitive. Any questions for Andreas before we close this afternoon? Yes.
So you mentioned that there was one of the quotes that. Sorry.
No worries.
Thanks for the talk. There was one of the quotes that mentioned redistribution. So I guess that's bringing parts of the benefits of selling at higher prices back to the consumers. I wonder if you've looked at how they do it in Canada and the US, because I think they might do that. So Canadians export hydro to New York, essentially. And then the Canadians get the advantage of that, the consumers.
Okay, that's I did not.
I'm not sure, but I think that's might be the case.
Okay, yeah. So I did not look into that. I'm only looking at the 3 countries at the moment: Germany, Scotland, and Norway. But obviously, it's really helpful to see a way forward, because that's something that I was asking a Norwegian politician. The question was, currently it's normal for the cost to be distributed 50-50 between each partner who's involved in the project. So I was asking, would there be any chance that more money goes to, so that Germany, for instance, who would be happy to receive some hydroelectric power in case there's a dark dull. So would there be any chance that Germany pays an extra, which is then redistributed? And he said, well, it's not been considered at the moment. So it would be really good to see an actual example of that. So thank you very much.
Thank you.
No, thank you for that. Any other questions for Andreas? Yes, please.
So the 2 projects you're looking at now, they're both funded by the owners of the networks. They're funded by SSE or by TenneT, or is this question of who pays, does it apply to interconnectors that are owned privately, like by like investment groups and stuff like that, or is that a completely separate question?
It's a central question of how I'm looking at these interconnectors. So I'm looking, so the general field that I'm looking in is large technical systems, but I want to assess the empirical data through the question of cost allocation, like how are the costs redistributed in these networks, who pays for them. And with the 2 projects that are existent there, they are both state-owned projects. So that's in the one to Germany, that's 50% Statnett, which is the Norwegian transmission system operator, and 25% KfW, the bank, and then 25% TenneT, which is a transmission system operator in Germany, which is state-owned by the Dutch state. And with the other link, North Connect, so North Connect is a bit different. The ownership is distributed among several smaller companies, which are municipally owned. Vattenfall is, for instance, included there. That's the only state-owned actor, but Statnett is not included in that. And many say that this might be a reason why this project doesn't go forward, because in Norway, in general, state-owned projects are favored. in order to protect their energy system.
So this issue doesn't exist as much where there's non-state owners.
So with Norway, there's no interconnector where there is a non-state actor involved. So that's quite a challenge at the moment. And with Great Britain, to finish that point, with Great Britain, it's all owned by third parties. So it's the complete opposite. Because Ofgem decided that, oh no, BICE decided that, I think it was BICE, decided that it's more protective for the customers if there's a maximum level of competition in the ownership of these links. So they said it's not good if a transmission system operator, for example, has a monopoly on that or is involved in that. So it's all on a merchant base.
Great, thank you. Alex,
Just very, very, very
very short one, yeah.
just very building on that. That
Microphone, Alex.
Sorry.
Yeah, so just building that last point, while that's clearly been true in terms of, I guess, a political decision, do you think that might change in the context of the world that we're in now and the insecurities we have, and there might have to be a rethinking in terms of the balance between competition and having more sort of state intervention just purely to protect supply for us?
Yeah, that's a really good question. That I think that also came up when Nord Stream was attacked. So the two pipelines. So it's a general question of what should be the ownership in general. So, different example in my hometown in Hamburg, we have a discussion at the moment whether the Chinese should own part of the harbor because they want to invest in one terminal at the harbor. And the state decided that this investment is limited to a maximum of 24.9%, so that the Costco has no decisive power in the operation of that terminal. So in general, it's a question, but it's also a question of overprotectiveness and separation from the market, because there's also the argument of creating security through more integration with other countries and creating the exchange. So it's an open discussion which I unfortunately have no answer about.
But you will have by the end of your PhD.
I hope so.
Let's show our appreciation to Andreas. Thank you very much. So thank you very much. I'm sure you, like me, would agree we've had a very interesting and very varied session this afternoon. A lot of interesting presentations. Thank you very much to each of the presenters, to Arshad, Mohammed, Taimur, and lastly Andreas. Very valuable PhDs. Keep working hard and produce some good results that we look forward to hearing more about at future ETP events and also at academic conferences as well. I've been Graham Burt from the University of Strathclyde. Thank you very much again, and have a good afternoon. Thank you.